All right. Glad you guys are still watching. In this lecture, I'd like to just talk about how do you interpolate. So it's a simple algebraic operation that we'll be doing here, but it's something that you're going to be doing a lot in the class. Now, some of you may prefer to interpolate using a computer program on your calculator, which you're welcome to do. That's actually what I like to do. An alternative method, though, for those of you who don't have the computer program built into your calculator, or you don't want to spend the time figuring out how to program your calculator to do that, you can use a manual method. It'll take a minute or two longer for you to calculate it this way, but it'll still get the job done. Alright, so what do we mean by interpolating? So what we're doing is, based on the surrounding data points, we're going to be prescribing a value to something basically as a guess. Now, I say guess here with some reservation. It's an educated guess, and we make some assumptions when we solve for these points using interpolation. So let me give you an example of what I'm talking about. So let's say we have values of x and y, and we'll prescribe some more thermodynamic meaning to these later. I don't know, so let's say this is 1, 2, 3, 4, and 6. But we don't know what that property is. So using the surrounding data, so using the corresponding values of 1 and 4 and 3 and 6, we should be able to predict what this value of y is for a value of 2. And it doesn't have to be whole numbers either. We can also calculate it for different decimal point values as well. Right? So let's do this simple example, and then we'll do a more realistic example here in just a minute. Alright, so the equation that we're going to be using to interpolate, we'll just use this one. Y minus y naught over x minus x naught equals y1 minus y naught over x1 minus x naught. So you may recognize this as being a form of finding the slope of a straight line, right? So if you know here, this is x naught, y naught, those are the coordinates of that point. This is x1, y1. We should be able to determine on this line any value between those 2 points, assuming that it's linear between the two. So this would be x and y. Alright, so x and y are the values we may or may not know. So in this case, let me show you what I mean here. In this case, this is going to be the value of x. Okay, so this is x naught. This is x1, and this is x, and we happen to know x. This is y naught, this is y1, this is y. We don't know what y is. So let's, using this same logic, let's plug the values into this equation. So y in this case, we don't know. Y naught in this case is 4. X, we also know, is 2. X naught is 1. And this is equal to y1, that's 6, minus y naught is 4, divided by x1, which is 3, and x naught, which is 1. So we can solve for y. And you can do that, so y minus 4 is equal to 2 over 2 times 1. So this is equal to 1, y is equal to 5. Alright, so that's how we would interpolate something. And keep in mind, when we make these assumptions of interpolating, we're assuming that the points are close enough together, so the distance between x naught and x1 are close enough together that we assume that it's a straight line. Some of these thermodynamic relationships, though, are not always a straight line, but we're assuming that they are a straight line, and that interpolation is going to give us a close enough value to the real value. So let's use some actual thermodynamic values. So let's go, if I go to your tables, and we'll do some examples here where we actually look at the tables together in the next few lectures, and we learn how to use them with each other. Okay, so let me just look at the saturated water table, and I'll look at the saturated water pressure table. Okay, and I'm going to interpolate to solve for the saturation temperature of water at 60 pascals. So what's the saturation temperature of water at 60 pascals pressure? Well, if you guys look in your table, you're not going to find that value. So what we have to do is we have to interpolate. In the table, we have the pressure above that at 50 kilopascals. So this should be kilopascals, sorry. Let me fix that. This is kilopascals. So at 50 kilopascals, we know that the saturation temperature is 81.32 degrees Celsius. The table also provides us that at 75 kilopascals, our saturation temperature is 91.76 degrees C. What we are interested in finding is this T saturation at a pressure of 60 kilopascals. And keep in mind, again, we don't have this value in the book. So we don't have this value in the book either. So we're using the surrounding data and assuming a linear behavior so that we can solve for this saturation temperature at that pressure. So using the formula we developed, so let me rewrite the formula here so that you can follow along clearly. We're saying that y is equal to y naught plus y1 minus y naught times x minus x naught over x1 minus x naught. Now we can replace these variables now easily with whatever we are interested in. So what we're interested in is finding T saturation. Y naught would be the saturation temperature at point 1, so that's 81.32 plus the difference between y1 and y naught. So y1 is 91.76 degrees Celsius minus 81.32. All right, and that's multiplied by x, which we happen to know. We want to find it at 60 kilopascals, minus x naught, which is 50 kilopascals, divided by x1, which in our case is 75 kilopascals, minus x naught, which is 50. So you could run this calculation and you'll see the saturation temperature at this pressure comes out to be 85.5 degrees C. And so kind of a rule of thumb too or actually should always be the case, is that the temperature that we're calculating here had to be between the ranges of 81.32 and 91.76. Okay? It can't be above that, can't be below that, since we're assuming it's a positive linear slope between those values. So as we increase the pressure, the saturation temperature was also increasing. So it had to be between those two values. So if you did this calculation in class, a good check for you is to make sure that it's somewhere in between 81.32, 91.76. So for future reference, I'm no longer going to show my interpolation work. I will just mention that I did interpolate, and I'll be expecting you guys to be able to perform the same calculation without the additional work shown. All right, so now let's apply some of these ideas. Let's look at using the thermodynamic tables to solve some problems, and let's understand how we can use them for actual different problems.